Hello, everyone. Welcome to the Digitalized in Stockholm 23. Today, I will present our project entitled Faster Than Real-Time and High-Resolution Simulation of Fluid Flow in Engineering Applications in the Climate as a pilot. So this is the Digital Futures Research Pilots project. And my name is Wei Liu, and I'm an associate professor at the AB School KTH, and I'm the PI of the project. And associate professor Ricardo Villanueva is a co-PI of this project, and he's from the School of Engineering Science, KTH. So, as we know, the fast and high resolution prediction of heat and mass transfer plays a critical role in many engineering applications. And using the indoor climate as an example, so in emergency management, if safe simulations of the smoke transport is in real time, more faster than real time, the rescue and evacuation plans could be made to minimize casualties. And besides, HVAC system should be continuously adapt to create desired indoor climate with minimal energy use. And its real-time control requires real-time prediction of air parameters for system operation. And the conceptual design of indoor climate generally involves numbers of design scenarios, and the prediction for all the scenarios should be fast due to the limited time and budget. And all the simulations should be high resolution so as to capture the detailed contaminant transport, such as this person-to-person particle transport in this animation. And super resolution is a promising approach for realizing fast and high resolution flow simulations. And borrowed from computer vision and image recognition, super resolution refers to techniques that obtains a high resolution image input from a low resolution input. The same concept could be applied to flow fields by treating them as images, but there are still challenges in real engineering applications. So first of all, how to obtain cost grade as the input. So we can either use the experimental measurements. It is reliable but expensive, and we need to find the least measurements to give a feasible input field. But anyway, such measurements are not realistic in engineering applications. And another way is a cost-grade CFD simulations. But if we compare a cost-grade CFD results with a low-resolution photo, the difference is that a low-resolution photo just has no quality, but a low-resolution flow field obtained by this kind of cost-grade CFD simulations might be associated with wrong physics. And even for the transient airflow, super resolution fields in extrapolating the flow fields, which belong to a different statistical distribution. So this study aims to solve the two challenges that the state-of-the-art super resolution models face. So the first objective is the development of fast numerical and inexpensive experimental approaches for obtaining feasible no resolution flow data as input for super resolution. So we plan to create an output by direct numerical simulation or LES maybe, and the input by mapping the DNS data to cost grade and Reynolds average and Navier-Stokes simulation, the RAND simulation with a cost grade. And the second goal is the further development of the super resolution for predicting transient indoor airflow, where extrapolation of the flow fields involved. And to take care of the transient indoor airflow, this project plans to develop a hybrid, recurrent, and convolutional neural network. And the co-PI's previous work has shown the feasibility of using a particular type of RCNN, the non-short-term memory network, to predict the temporal dynamics of turbulence. So we will implement those by using TensorFlow and the OpenFOAM. So overall, this project will have three packages. The first one is the literature review. We only investigate the state-of-the-art super resolution models and cost grid techniques. And then the second package is data collection. So we will develop a database by using the high fidelity safety simulations and runs data indoor airflow. Okay. but not limited to that. And we will then in the third work package, we will try to develop, train, and validate the super resolution models. So we will probably, hopefully, we can develop 2 models for the fast prediction of the indoor and outdoor airflow. So our literature review first found that the methods for non-intrusive sensing urban flows could be adopted in our study. So the POD could be used to decompose the velocity and the pressure fields into a set of deterministic spatial functions and modulated by the random time coefficients. So once the random time coefficients were predicted, the instantaneous flow and pressure fields could be reconstructed. And the first reconstruction method used to measure all temp pressure as input and output the random time coefficients for the flow field by this non-short-term memory network for reconstructing the flow field directly. And another approach outputs the random time coefficients for pressure field first, and then determines the flow field by using convolutional neural network. So this study will adopt cost-grid safety results at the input where physical error may exist and need to be handled. And for obtaining the input data, we will make use of a fast CFD algorithm, the standard incremental pressure correction scheme. And this scheme split the momentum equations into 2 equations. So one for the advection term, diffusion term, and the source terms implicitly, and then the pressure term explicitly. Then we solve the pressure difference terms continuously. We solve the pressure difference term and the continuity equation together by using the pressure projection method. Then we can combine the solution to get a final answer for the Navier-Stokes equation. Since the advection term is solved by the semi-implicit scheme, it will not introduce any significant numerical diffusion. And then we will also adopt a RANS model to simulate the turbulence. So this is implemented in open form. And then to develop a cost grid for this safety simulation, if we have a look at the numerical error, for example, if we apply a first order upwind scheme, then we can find the extra coefficient added to the diffusion term, okay, which is called the numerical viscosity. And then this value is proportional to the grid size. So the cost grid will introduce more significant numerical diffusion and decrease the prediction accuracy. So we propose to start with a grid independent, the grid that provides the grid independent solution. And then we can caution the grid where the numerical error is significant. And finally, we can obtain a cost grid with the same accuracy of these fast safety simulations. And then also for the input, but for the output data as well, we can use this database of the flow through a simplified urban environment. So those data was obtained by this NEC 5000, which is a high scalable spectral element computational fluid dynamics code for solving the incompressible Navier-Stokes equations. So this study used like 205,000 elements to discretize the domain, and there is a total of 105 million grid points. Okay. So this model is simulated by a well-received LES, and it has a good agreement with the DNS data. And the right figure shows the instantaneous visualization of the flow around 2 all-mounted obstacles. Okay, so this is the one data we use, and there's around 1,000 instantaneous flow fields. And another is we will also use the indoor flow. So here we consider the turbulent flow in a simplified indoor environment by using preliminarily the LES, large jet simulation. So it is basically a mixed convection where we have the jet and also thermal plume from the box. So we use the OpenFOAM to do the simulation, and it so far has very good agreement with the experiment data, but if it agrees with the DNS data, it will need further investigation. So that's what we have done so far, and thank you for your listening.